Hello and welcome to the Autodidact Scientist Algorithm series. I'm going to be giving you an intuitive insight into a variety of algorithms that are used in machine learning. I'm your host, Rich Gregson, and before we get started, I would greatly appreciate it if you would like this video and subscribe to the channel. The algorithm that we're going to be covering today is the decision tree. A decision tree is a supervised machine learning model used to predict the targets by learning decision rules from features within a dataset. As the name suggests, we can think of this model as breaking down our data by making a decision based on asking a series of questions. And before we dive in, let me clarify a couple of key terms that will ultimately help you understand decision trees a lot better. The first one is a root node. Now this represents an entire population or data set, and this further gets divided into two or more homogeneous sets. Splitting, that's the process of dividing a node into two or more subnodes. A decision node is when a subnode splits into further subnodes, and a leaf or terminal node, which they're pretty much the nodes with no children where no further split is possible. Pruning is what we do is the name of the process where we reduce the size of the decision tree by removing nodes. A branch or a subtree is simply a subsection of a decision tree, and a parent and child node. So they're the nodes which are divided into subnodes. The original node or the higher level node is called the parent, and the ones that it splits into are called the childs. So what is a decision tree? The more modern term for a decision tree is CART, C-A-R-T, and that stands for a classification and regression tree. And that term was introduced by someone called Leo Breiman, who was a statistician, and he worked pretty much his whole life on decision trees and random forest algorithms. Now, what the CART model is a binary tree, and that is constructed by recursive partitioning. As you can see on screen, we've got a very basic visual representation of a decision tree. And at the top, in brown, you can see a root node. Each root node represents a single input variable, usually known as x, and the split point on that particular variable. The ones in green at the bottom, the leaf nodes, they're the ones that contain an output variable, and we usually assign y to them, and they're used to make predictions or classifications. So in its very bare bones form, you could argue that it's a fancy if else statement, but let's just go over how they work. So when a model is given an input, the tree is traversed by evaluating the specific input starting at the root node at the top. Now, a learned binary tree is actually a partitioning of the input space. You can think of each input variable as a dimension on p-dimensional space. The decision tree splits this up into rectangles or some kind of hyperrectangle with more inputs. One of the rectangles receives new input that is being filtered through the tree, and the output value for that rectangle represents a model's forecast. So this offers you a sense of the kind of choices a CART model can make, such as box decision borders. So going on from that, how do we know what the optimal splitting point is at each node? So the data that is received is divided based on the characteristic that produces the greatest information gain, which is known as IG. Starting at the root, the splitting technique is then repeated at every child node in an iterative manner until the leaves are pure, or the samples at each node all belong to the same class. In actuality, This may produce a deep tree with several output nodes or leaf nodes, which is easily conducive to overfitting. So as a result, we normally seek to prune the tree by establishing a cap on its maximum depth. So how do we maximize information gain? In order to split the nodes at the most informative attributes, we need to define an object function that we want to optimize through the decision tree algorithm. Now, the objective function is the equation you can see on this slide. F is the feature to perform the split. dp, dleft, and dright are the data sets of the nodes. I is the impurity criterion. N is the total number of samples at the decision or parent node. N left and N right are the number of samples within the child nodes. Now, entropy and Gini impurity are the selection criterion for decision trees. And what they do is essentially help you determine what is a good split point for the root or the decision nodes. And they can be used for classification and regression trees. Generally, the lower the impurity, the more information is gained from the split. And as you can see in the tree image on screen at the moment, that has been built on the classic iris dataset, and entropy is calculated at every split. The equation that you can see on screen is for a binary tree, which means each node is subsequently split into two other nodes. If you have a decision tree with more nodes, you would simply sum the impurity of all those nodes. So how do we prune a decision tree? Like in all other parts of machine learning, there's an underlying rule: simplicity is superior. So there's a number of ways we can make our decision tree model simple. The first one is stopping criterion. And what we do when we use a stopping criterion is instruct the decision tree to stop splitting at a certain value. The most common stopping criterion is to use a minimum count on the number of training iterations assigned to each leaf node. And this count will be tuned to your specific data set. So if you use a value that's too specific, your model will tend to overfit, and vice versa. If the count isn't specific enough, you'll get an underfitted model. Now, the stopping criterion is crucial because it can significantly affect how well your tree performs. So when you're setting things like the max depth, the minimum sample split, the minimal sample lead, and the max feature parameters, what you're actually doing is controlling the splitting of a decision node to the benefit of your model. The next one, pruning. Now, as the name suggests, all you're doing is chopping the tree back. Now, what happens in a decision tree is that data will be periodically divided into smaller and smaller subsets by the algorithm until the final subsets are homogeneous with in regards to the outcome variable, or the output variable, shall I say. So in actuality, this frequently results in the final leaf nodes having very few or even one data point. Now, although the tree has learned the data exactly in this instance, it might not be able to predict on a new data point which contains a slight variance or minor difference. So what we have to do is work through each leaf node in the tree and assess the impact of its removal using a holdout test set. A holdout test set is the quickest and simplest pruning technique. The leaf nodes are eliminated when the overall cost function for the entire dataset decreases. The pruning and the stopping criterion help with the trade-offs involved when using a decision tree, and they can be boiled down to a few guidelines. The first one, for best accuracy, minimum error pruning without early stopping is usually a good choice. For a compromise between the accuracy and interpretability, try smallest tree pruning without the early stopping. And to produce an even smaller tree or reduce the running time while allowing accuracy to decrease, you can turn on early stopping. So what are the advantages and disadvantages of decision trees? Now, decision trees can inherently perform multi-class classification. They provide the most model interpretability because they're simply a series of if-else conditions. They can handle both numerical and categorical data, and nonlinear relationships in the features of your dataset do not affect the performance of the decision tree. Now, they do come with a couple of disadvantages, of course. Those being a small change in the dataset can make your tree structure unstable, and that can lead to variance in your output. Decision tree algorithms can create underfit trees if some classes are imbalanced. So please, before you fit a decision tree algorithm to your dataset, make sure it is balanced. And large trees can sometimes become very difficult to interpret, and this is because the bias towards splits on features that have the greatest number of levels. Now, since a decision tree classifier tends to overfit in most cases, it is preferable to replace a decision tree classifier with principal component analysis for datasets which have a very large number of features. I will go into principal component analysis in another video, but that is just a word of advice for the time being. So we've spoke a little bit about the advantages and the disadvantages of decision trees. So how do decision tree classifiers and regressors, how are they used in real life? One of the most common applications for them is in biomedical engineering. They're used in places like the DA, financial analysis, economic product development, and they're also utilized to comprehend customer satisfaction levels, the firm's finances, and other associated behaviors. Decision tree classifiers are also used in system design and in physics, especially around particle detection. It also finds application in manufacturing production, wherein it can be put into quality control, anomaly detection, and semiconductor manufacturing, for example. And that concludes our video on decision trees. So I hope this video helped you get an idea of how a decision tree works. If you have any questions, comments, or any feedback whatsoever, please contact me personally through my social media channels, or alternatively through the Autodidact social media channels. And of course, please support the Autodidact Sciences team by liking and sharing this video, as well as subscribing to the channel. Thank you very much for watching.